Lisa Goddard received her PhD in atmospheric and ocean sciences from Princeton University in 1995, just at the time when climate science and its importance was really beginning to gain public attention. She went out to Scripps Institution of Oceanography at the University of California, San Diego, to work with a forecast group, the International Research Institute for Climate and Society. This group moved to Columbia University in 1999 as part of the Earth Institute. Lisa also serves as an adjunct associate professor in the Department of Earth and Environmental Sciences at Columbia. In addition to her active research and numerous publications on climate, she sits on national and international advisory panels. So please join me in welcoming Lisa Goddard.
Thank you all for coming out tonight. The title of my presentation is given on the screen above. I'm primarily going to be talking about the roles of natural variability and human-driven change in near-term climate prediction. And the three things that I want you to remember from this talk, because there will be a test later, the three things that I hope that you can take away from this discussion are first of all, an appreciation of the differences in strength of climate in terms of natural variability versus the human-driven change over the last century. The second thing would be, at least broadly speaking, the mechanism of some important natural variability in the ocean. And thirdly, how that natural variability in the ocean impacts climate in this part of the United States. This slide is actually the only forecast I'm going to show in this talk. Yeah, should we turn up the mic? This slide, as I just said, is the only forecast I'm actually going to show in this presentation. This is some output from the fourth assessment of the Intergovernmental Panel on Climate Change that was released last year. And what's shown in this graph is the globally average temperature, both the observations over the 20th century and the projections for the 21st century. And as I'll describe later, although this information is extremely meaningful, it's somewhat incomplete for a lot of planning purposes. So we have up to year 2000 the observations. Those are shown by the black line. And the values on this axis here are relative to the climate period of 1980 to 1999, so the last 20 years of the 20th century. And so you can see the slowly increasing global temperatures over the 20th century. And then there's these projections that go up from there on in the 21st century. And the different colored lines has to do with our with various scenarios. We refer to them as scenarios, which has to do with our assumptions on how greenhouse gases are likely to change in the 21st century. The orange line, with the yellow envelope around it, is what the global climate, what the global temperature would likely do if we were able to hold the greenhouse gas concentrations fixed from the 2000 level. Since that's obviously not going to happen, we're going to just completely disregard that one right now. The other three are three assumptions on how the greenhouse gases might increase in the 21st century based on different emissions that are related to energy use and technology advancement. And so we have a relatively conservative scenario, a somewhat intermediate scenario, and then a more extreme scenario for how those concentrations increase over the 21st century. The solid line that you see in the middle, because these projections are based on about 20 climate models. So what you see in the middle, the heavy line, is the average of those 20 model projections, and then the envelope about that is the range of those models in global temperature. What's clear is that up to about 2030 or so, all of those scenarios, those different assumptions and emissions, pretty much line up on top of each other. So you might ask, well, why do we really care then? What are the different scenarios? And that's because going past 2030, there's some pretty notable and important differences in the implications for global temperature. But they do all line up for each other, on top of each other for that first 20 or so years into the future. And not just on the global average, but also in terms of the patterns of climate change as well. So these maps here are showing you, again, 20-year averages relative to the last 20 years of the 20th century. And the colors indicate that increase of temperature, again, for the average of the 20 models. So these are the three different scenarios, averaged between 2011 to 2030. And a point here, again, is just that those patterns and the magnitude of the warming does look pretty similar between the scenarios. What's not shown in these maps is the uncertainty about those projections regionally, because it will be larger than what we see in terms of uncertainty on the global scale. But an important piece that's missing from these maps, and at least in respect to what I'm talking about this evening, is how the slowly varying natural variability in the climate system could modify these projections, especially regionally. What these climate change projections are intended to do is to give some sense of what the climate response is to increasing greenhouse gases. And that mechanism we understand pretty well. It's related to the greenhouse effect. Many of you have probably seen this or are quite familiar with it, but I run through it for those of you that might be less familiar with it. So the greenhouse effect is a naturally occurring phenomenon in our climate system. We have greenhouse gases in our atmosphere that have pretty much always been there. Carbon dioxide and water vapor are the most abundant. So the idea is that, well, all molecules, or atoms for that matter, have particular energies or wavelengths of energy that they're receptive to, that they want to absorb, and that they'll re-radiate out again. And the fact that we have these greenhouse gases in our atmosphere, they're not particularly interested in absorbing the energy at the wavelength that's coming from the sun, that visible and ultraviolet energy. So that goes right through. Most of it's absorbed by the Earth's surface, and it warms up the Earth's surface. As the Earth warms up, it starts to radiate heat. And it's that heat wavelength that the greenhouse gases do like to absorb, that they're very open to. So those greenhouse gases, they absorb the heat, and then they re-radiate out, but in all directions. So some of it's radiated back to space, but some of it's radiated back to the Earth as well. So the greenhouse gases are basically feeding in more energy to the Earth's surface than we would have if they weren't there. And that difference increases the surface temperature of the Earth about 60 degrees Fahrenheit relative to if they weren't there. So it gives us a nice habitable climate. And the cycling of carbon dioxide has been going on pretty naturally for millennia between the Earth and the atmosphere and the oceans. What humans have been doing over the last 100 or so years is basically disrupting that balance, artificially extracting carbon from the Earth in the form of fossil fuel, burning it and releasing that carbon dioxide into the atmosphere. And so that's increasing the amount of greenhouse gases in the atmosphere. It's increasing the amount of molecules that can absorb heat and send more energy back into the surface of the Earth and warm up the surface of the Earth. That's the enhanced greenhouse effect. And so it's not the greenhouse effect itself that's causing global warming, it's this enhanced greenhouse effect. But the climate system is not just this passive bathtub that warms up. We have a very active climate system, and the redistribution of heat in the climate system by the atmosphere and the ocean and how those interact lead to variable climate. So we have climate varying on all time scales. So let's look at how that's played out over the 20th century. This time series here is the globally averaged annual mean temperature. So the black line is the year-to-year measurements in global temperature. And all we've done is to then run a sort of a smooth line through there, try to get rid of the year-to-year wiggles. It's basically smoothing it at about 10 years. So that red line is then reproduced in the center panel. I'm going to call that the global climate change signal, but it's not synonymous with the temperature increases due to increasing greenhouse gases. And in fact, in the early part of the century, we believe that it's quite possible that much of the temperature variations were due to natural processes. But in the latter decades of the 20th century, those increasing temperatures are due to the dramatic increases in carbon dioxide. The bottom time series is just this difference between the black and the red that's in the top plot, so just the wiggles about that red line. And that's year-to-year variations in global temperature. But you can see that the dominant signal in global temperature is this slowly varying and increasing temperature signal. Looking at this at a more regional scale, we repeated a very similar analysis over Colorado, but not Colorado specifically. It's about a 10 degree by 10 degree box. Colorado's sitting within it. And so we're just averaging the temperature over this big Colorado containing box. And so the black line again is the annual temperature measured over that box. And we've again smoothed it. That's the brown line on the top graph. What we're interested in now that we're looking at just a region is how much of that slowly varying time series, how much of that brown line is related to the global climate change. And if we do that analysis, we basically look at the portion of that brown line that's related to the global climate change that I just showed previously, we end up with this red line here. So over this Colorado region, that's the climate change signal over the 20th century. But there's a substantial part of that brown line that is not related to the global climate change, and that's the green line. So that's what I'm calling natural decadal variability. So there are a few things that I want you to notice in the relative magnitudes of these different time series. First of all, for the red line, let's go back to the global time series. If you notice the magnitude of the temperature changes of the 20th century, it's the exact same scale as is on this, pretty close to the same scale that's on this graph as well. So the climate change signal over this Colorado region is pretty similar to the global climate change signal over the 20th century. And that's looking at about 2 degrees Fahrenheit or so over the century. But if you look down at the green line, who's varying at about 10 or 30 year period, you can get that 2 degree Fahrenheit change in a matter of 10 years, as opposed to a century. The bottom curve, the blue line, is the year-to-year variability that definitely dominates the time series over this region, and in fact over most regions. And you might notice that the scale for the blue line is twice what it is. So it really is much larger, the year-to-year variability, than these slowly varying time signals. And that does have some implications for how we talk about year-to-year climate, because if we just have a particularly hot year or a particularly cold year, you can't use that one instance as proof or a negation of climate change, because that's only 1 year, and natural variability on this year-to-year timescale is completely dominant. But this natural variability, both year-to-year and decadal, is playing out over this slowly increasing trend in temperature. And that definitely does have implications for how often in the future we're going to see these extremely warm or extremely cold years. For precipitation, it's a somewhat different situation, but a similar message. So we've done this exact same type of analysis. Here now, when we try to look at what part of that slowly varying, what part of this slowly varying time series is related to the global change signal, it's extremely small over the 20th century in this region, extremely small. So most of the low frequency variability in this region is natural decadal variability, again occurring on about a 10 to 30 year time scale, and you can really see a lot of the very major periods in this time series. For example, this Dust Bowl period in the 30s, the Great Plain drought in the 50s, there were some drought conditions in the 70s, and then what's been going on recently. But again, the year-to-year variability really is the dominant part of this time series. So what you have is this decadal variability modulating the year-to-year variability, the frequency or the intensity of wet or dry years. Now, it'd be really great to be able to predict this decadal variability piece. We have these climate change models that are trying to get at the red lines. We have seasonal to interannual predictions that are trying to get to the blue variability, largely based on El Nino and La Nina. And we're working on the green lines. But the green line is going to impact our realization of the trend, certainly over the next 20 years. And it's also going to impact the impacts of the year-to-year variability due to ENSO. So one question we have is, well, let's look at what are the possible causes of this low-frequency variability, because if we don't really understand the causes, then it's going to make it even that much more difficult to predict. So let's look to the possible causes of that variability. In terms of slowly varying climate, we typically look to the oceans. And that's because they vary on so much slower of a time scale than the high-frequency weather and even seasonal variations in the atmosphere. And those changes in the patterns of temperature in the ocean do affect atmospheric circulation, so they affect regional patterns of temperature and precipitation. And there are two pretty dominant patterns, or what we call modes of variability, that are known to vary on this decadal to multi-decadal timescale, and that's listed here: the Pacific Decadal Oscillation, PDO, sometimes referred to instead as Pacific Decadal Variability, and also the Atlantic Multi-Decadal Oscillation, AMO, or again, Atlantic Multi-Decadal Variability. So what I'm going to describe next is what they are, how they affect the regional climate, and what is our ability to predict them. Typically, when we go to describe modes, we're looking at patterns of variability as well as how those patterns vary in time. So I'm starting with the patterns here. And on the left-hand side, that pattern represents the positive phase of the PDO. The colors are temperature at the surface of the ocean. So in the red colors, you can see in this particular map here, we have warmer than average temperatures in the central and eastern tropical Pacific, and cooler than normal temperatures in the North Pacific. And then overlaid on those temperatures are low-level winds and sea level pressure, but we're mainly going to focus on the temperature signature right now. This is then the negative phase of the PDO, which to a large degree is just the reverse sign of the temperature anomalies. The time series of the Pacific Decadal Oscillation looks like this, and you can start to see why people are not really comfortable calling this an oscillation. It's not particularly regular, like you would expect an oscillation to be, but it does have these positive and negative phases. These positive phases that have been shaded in these red bars, and the negative phases in the blue bars. But this has got a lot of year-to-year variability in it, and it's not particularly regular, and that does make it somewhat difficult to predict, because even if you know that you are or have been in a positive phase, it's very difficult to know how much longer you're going to be in that positive phase. Or because of the amount of year-to-year variability, if you happen to have switched into a particular year that looks like the negative phase, is that just year-to-year variability, or are you likely to be there for a while? And those of you that are familiar with El Nino and what that looks like in the tropical Pacific might actually recognize this pattern here, because it does look reminiscent of El Nino, the fact that you have these warmer than average temperatures in the tropical Pacific. And it is, in fact, thought that the El Nino and La Nina phenomenon are a very major part of influencing the PDO. But it's also thought that there are other mechanisms that are very important to the PDO as well. And so again, this makes it extremely difficult to predict the Pacific Decadal Oscillation, and even somewhat difficult to understand what's going on with it. For the Atlantic multidecadal, it's also got positive and negative phases, and it's somewhat more simply indexed than this complicated pattern that I showed for the Pacific Decadal Oscillation. So I haven't even shown a map here. This top short graph is actually measurements of the temperature with these positive phases and negative phases. And the Atlantic multidecadal oscillation, this time series, is just defined by the temperature over the North Atlantic. So when it's in a positive phase, that means the North Atlantic is warmer than average. When it's in a negative phase, the North Atlantic is colder than average. And that's pretty much how that's defined. And we can see that it's had these variations over the last 150 years or so. But because this Atlantic multidecadal oscillation, the changes in the North Atlantic temperatures influence temperature and precipitation over land, it influences things like the growth of trees. So tree rings have been used to try to reconstruct the Atlantic multidecadal oscillation. And so in the period of overlap, those two time series agree pretty well. This is not measurements of temperature. This is a reconstruction based on tree rings. But since these agree well, then you can go ahead and push the reconstruction back further. And this goes back actually into the 16th century, showing that over at least the last few hundred years, we've seen these up and down, positive and negative phases of temperatures in the North Atlantic Ocean. Again, this is highly not regular. It does flip back and forth between positive and negative, but not as an oscillation. But at least here, we think we have a mechanism. And this is, if you're keeping track, this is your second take-home point. And we believe that the Atlantic multidecadal oscillation is related to changes in the thermohaline circulation. Some of you might be more familiar with the term Atlantic conveyor belt, maybe from Day After Tomorrow or something. But it's basically a density-driven overturning circulation. The density in the ocean is related to both temperature and salinity. So that's the temperature for the thermo part, salinity or salt for the haline part. And so if you have particularly cold or particularly salty water, that's going to be more dense. So it's going to be a heavier parcel of water. If the parcel of water is warmer or more fresh, it's going to be lighter. And so the idea of how this overturning circulation works is that you have this cold water up at high latitudes. You're forming ice. Ice is has no salt in it. So when you form the ice, you leave the salt behind. So you have this relatively very salty water that's now heavier than the water below it, and it sinks. And as that water sinks, it then starts moving equatorward. But as this water sinks, it needs to be replaced by some other water, which is replaced by this northward flowing surface current that's bringing water from the tropics. So you have this warmer water that's coming from the tropics, and particularly in the subtropics where there's a lot of evaporation. It's not only warm, but it's really salty. And so as this water is moving towards the high latitudes, it's happening somewhat slowly, and you're losing heat all along the way to the atmosphere. So it's getting colder and colder, getting more dense as it moves to the high latitudes. But at the same time, it's raining, and you're going underneath the Atlantic storm track, so that's adding fresh water, that's making it a little bit less dense. Right now, the temperature part is winning. So you do have this overturning circulation. And we believe that it's and you can see also that because this is moving this warm water from the tropics, this is a really important mechanism in transporting heat out of the tropics into the mid-latitudes. And so variations in how strong that circulation is, variations in how much heat is being brought out of the tropics is going to influence the temperatures of the North Atlantic. And so it's believed that it's the variations in this overturning circulation that are related to the AMO. And what's interesting over time, I mean, this is somewhat of a self-regulating mechanism, which is kind of nice. So you could think if the temperature, let's say the temperature goes up, that means that the density is going to get lighter. And so if the water parcels become relatively lighter, there will be less sinking. That means that there's less warm water that needs to move up from the tropics. So you're actually transporting less heat out of the tropics into the mid-latitudes, and the North Atlantic starts to get colder. As the North Atlantic starts to get colder, though, now your temperature of your parcel is going down. It's getting heavier and more dense. So now there's more sinking. So now you have to bring up more water from the tropics, and that's more heat transport into the North Atlantic. So now the North Atlantic starts to warm. But this is a really slow process in terms of this flywheel of realizing that something is sort of overshot and maybe it should slow down or it should speed up. This is not something that's happening on days or weeks like Hollywood would like us to think. It's actually a very slow process, and you can get the sense of that too from this time series. But there are other things that can add noise or aperiodicity to this signal, because this thermohaline circulation is not the only thing that's driving currents northward. The wind, the trade winds coming across the ocean are also driving northward currents. And so changes or variations in those winds can add some noise into the system. Changes in the strength or positioning of the precipitation pattern can also put noise into the system. Currently, the North Atlantic is warm. So currently we seem to be in a positive phase of the AMO. So how is this Atlantic multidecadal likely to affect regional precipitation? This is a map showing precipitation anomalies, precipitation changes when the North Atlantic is warm. And it's a model result. It's from a climate model. But many of the regions that are showing up in this have been corroborated by regional observations of how the precipitation changes when the North Atlantic is warm. So this is for the June, July, August season. And you do see these shifts in the regional precipitation. So for example, Central America is wetter than average. The Sahel is wetter than average. India is wetter than average. At the same time, the Philippines is drier than average. Parts of Northern South America are drier. Interestingly, there's this very large area of North America that seems to get drier than average when the North Atlantic is warm. The frequency of hurricanes has also been associated with the Atlantic multi-decadal oscillation. And this is a paper that was published in 2001. I believe that it was really one of the first documentations of this slowly varying changes in North Atlantic temperature. But what they're showing you here, this little inset, is the time series of the AMO up to about the late 90s in the negative phases and positive phases. And what it's showing you is that over a negative phase, you have relatively less hurricanes in the Atlantic than you do during the positive phase. And they estimate that at least twice as many hurricanes are occurring during the warm phase, during the warm North Atlantic, than they are during the cold North Atlantic. Again, since this paper was published in 2001, we hadn't quite moved into this warm phase that we're experiencing now. And it did warm up subsequently, and we had these very devastating hurricane seasons in 2004, 2005. So let's look at how these two slowly varying modes come together and impact drought, for example, over the United States. This is an analysis that was looking at the frequency of drought. So these are not looking at precipitation anomalies, it's actually looking at the frequency of drought. And the way that they've defined it is as 25%. So they're looking over the 20th century, assuming that wherever they're looking, 1 in 4 years is just defined as drought. And not every fourth year, but 1/4 of the years over the 20th century are the drought years. And they're just looking at how frequently those drought years are occurring in these different periods when you had either the Pacific decadal and the Atlantic multi-decadal oscillations in phase or out of phase. What is that relating to in drought frequency? And so the way that they've plotted these then, if 25% frequency is the expectation, in these red areas, that's where the drought frequency is increased. And in these blue areas, that's where the drought frequency has decreased. And this is all based on these time series of the PDO and the AMO over effectively the 20th century. And they've just carved out these time sections here where things were in phase or where things were out of phase and looked at the frequency. So admittedly, you don't really have a whole lot of cases going into this, but it is indicative, and I think fairly interesting as well. So what's really unfortunate for Colorado is that in all 3 of these cases, so in 3 out of 4 cases, at least most, if not all of the state has increased risk of drought through the record. It's only in this particular situation here, or at least in these cases that they've looked at, when the Pacific decadal is in a positive phase and the North Atlantic is cold, that you have a reduced frequency of drought. And you can pick out, again, some of the major climate anomalies that have really hit the United States. So again, here's the period of the Dust Bowl. This includes the period of the Great Plains drought of the, this is the 70s in here. What I think is interesting that actually goes beyond the time series that's contained in this, as I mentioned earlier, we're currently in a negative PDO phase and a positive AMO phase. So we might expect an increased frequency in drought, and in fact, the Southwest has had this prolonged drought problem since the late 90s. But recall, that's just an increased frequency of drought. There is still year-to-year variability, like this year, for example, that's playing out on top of that. So this is not, drought is going to happen every year. This is just drought is going to happen, dry conditions are going to happen more frequently in those periods. Focusing a little bit more down on Colorado, this is an analysis that was done by Colorado State climatologist Nolan Doskin. And what he was looking at here is the fraction of Colorado that's contained in drought, which is some sort of deficient measure of precipitation for some 48-month running period. And it just really pulls out the times through, since about 1890, these periods of very expansive and very prolonged droughts that have affected the states. And again, these same periods that I keep pointing to come out really obviously here. Here's the 1930s drought, the 1950s, 1970s. the more recent drought conditions. And so it's very frequent that Colorado is under some pretty substantial drought conditions. It's only these small windows when you don't see very expansive or prolonged drought, and those happen to be just those same little blue maps, those periods of the little blue maps that were up in the corner when we have this particular phasing of the Pacific and the Atlantic modes. So back to this slide here on these slowly varying modes of the oceans. We've gone through what they are and how they affect the regional climate. And what we haven't really gotten to is can we predict them? Now, not coincidentally, that's exactly what this meeting is about this week here at the Aspen Global Change Institute, is discussing the prospects for predicting these decadal variations. And in particular, the sort of modes that are happening in the Atlantic, because we think we kind of understand what's going on there. But being able to predict these decadal fluctuations, but in addition to the climate changes that are related to the increasing greenhouse gases. So how are these likely to come together and result in the climate that we're actually going to experience over the next 10 to 20 years? So can we predict them? Well, the short answer is not quite yet. I don't think that's really been strongly demonstrated, at least through the community. But there is some really promising research that's been coming out that does suggest a strong possibility for prediction on those time scales that might be available in the next few years, we're hoping. And that's certainly what the individuals in this room are working very hard on. But it's an extremely difficult problem. It's extremely difficult. And one thing that's very important to making these predictions is observations of the ocean. We need the observations of the ocean, since the oceans are involved in these modes, to initialize the predictions. And what that means by initializing the predictions is we need to observe what's the current state of the oceans and use that as effectively a starting point for our predictions. So we want to be able to capture whatever sort of inertia, like for example for the thermohaline circulation, whatever sort of inertia might be in that current ocean state, so that the prediction can evolve that forward in time, maybe for the next 10 or so years, and result in the ocean variability that's likely to impact our climate variability. So just as a final item, I wanted to give you some view of what these ocean observations are that are particularly relevant to this problem. And those are these what we call profiling floats. We call them Argo. And on the left is a schematic of how these Argo floats work. They look really big in this picture, but my impression is that they're about the size of a large man's leg, something like that. Like Kareem Abdul-Jabbar, you know, not. And so they have a little antenna sticking out the top. They sink down to about 2,000 meters depth, and they drift along with the currents for 10 days or so. And then they pop to the surface. And as they're rising to the surface, they're recording temperature and salinity along the way. And then they get to the surface, and they float there for about an hour, transmitting all that data they just collected to the satellite, which then beams it over to land to somebody's computer database. And then they go back down again, and they keep repeating this. This here on the right is an example of one of those profiles, the example of one of those data streams that one of those floats just popped up and happened to send out on May 15th, 2004. So the temperature with depth is this black line, and here's the salinity. And this complex structure is extremely important for ocean modeling and studies of ocean processes and mixing and things like that. But the spatial coverage of these Argo floats, and going down to 2,000 meters depth, it's what's really important. And so this is a picture of where those Argo floats were near the end of 2004. There were just over 1,500 of them. The different colors are the countries that are contributing these floats. You can see it's really an international cooperation to establish this monitoring system of the ocean. The United States is definitely contributing a very large portion of them. But also substantial contributions are coming from Japan and European countries as well. Now, this actually looks like pretty good coverage, and it's got the coverage, it's just not very dense. One of these dots is about the size for this map of Los Angeles, and it's a man's leg. So it's really not very, very dense in any particular location. Now, as of a week ago, well, first of all, in the recent years, they made the dots bigger, so it looks like. But there are over 3,100 floats out there now, which is really great. But what the color refers to here is the age of the floats. And so it's only the red dots that have been out there for 4 or more years. Apparently, the lifetime of these floats is only about 4 or 5 years anyway. So that means that at some point they need to get replaced. And it's just extremely important that this array of observations be maintained, not only for initializing our forecasts, but that it's there over time so we can actually understand the processes and observe the changes now and in the future of these ocean modes and how the ocean is changing over time. So I can't say enough about how important it is that we maintain this ocean array. So write your congressman. It's extremely important, and especially to this endeavor of doing decadal prediction. It's really quite crucial. So in summary, regionally, it's extremely important to remember that the decadal variability can be as large or even larger than the global climate change, certainly between now and 2030. The decadal variability will influence our experience of climate change and also modulates the year-to-year variability so that the frequency or intensity of adverse climate. The slowly varying conditions in the Atlantic do have a notable impact on the U.S. climate, and we think we pretty much understand the dominant mechanism of that variability, and certainly that's going to be key to trying to produce credible predictions on this timescale. And again, the ocean observations really are crucial for the starting point of these predictions, and they're also crucial for monitoring the global oceans and their variability, even understanding where we are now. So, thank you very much.